Welcome on the second day of the European Utility Week, and welcome to Theater 6 on renewable integration and how this renewable integration affects grid stability and what can we do about it to make sure we have a stable grid operation to avoid any difficulties with the integration of renewables. So we have a very interesting lineup of speakers today, as you can see on the monitor. We've managed to cover the entire value chain of electric energy provision, let's say, starting from generation side. We will have a presentation from Verbund Hydro. Over transmission side with the Austrian TSO represented here today. We will have two presentations from DSOs, from one French Enedis and Austrian Energienetze Steiermark. And we also have the research side covered to give us some new insights on latest developments. So my name is Anthony Zegers. I work at the Austrian Institute of Technology, which is the largest independent research institute in Austria. And I have the honor to moderate this session to walk you through this morning session. So without any further ado, I will not take too much time to close this introduction. I would like to immediately introduce Mr. Dorko Ilyačevski from Siemens, working on PV utility scale, utility scale PV, and who will give us his insights on how this utility scale PV will develop in the further future. And I'm happy to discuss the impact on grid stability in the course of this presentation. So maybe before we start, as a practical, some practical points, in case there are any questions in terms of comprehension, don't hesitate to ask this question during the presentation. We have this incredible, where is it? Yes, we have an incredible cube which I can pass around. So if you have any comprehensional questions, just raise your hand. I will come to you with this cube and we can deal with the question right away. In case you have any questions which would lead to any discussions, I propose to do this right after the presentation of the respective speakers. So I was aiming for 15 minutes presentation and 5 minutes questions. All right, Mr. Ilyačevski, I tried my best. The floor is yours.
Good morning, ladies and gentlemen. I hope you can understand me loud and clearly. Thumbs up? Yeah? Okay, very good. So I'm from Siemens, another Siemens guy today. My speech is about PV, photovoltaic, in utility scale. And where is my, yeah. And I want to give you an insight not only about the market, but of course about the market and future and trends, but also about techniques. Especially we are looking after grid stability, and here we are focusing very much on the so-called EBOP, electrical balance of plant. But before I'm coming to that point, and I will explain later on what is EBOP, first I want to introduce you my old friend, Mr. Socrates. And Mr. Socrates said, the secret of change is to focus all of your energy not on fighting the old, but on building the new. And this is a challenge for all of us, because you will face in this environment, especially with the very conservative utilities, you will see that they are holding very, very rigid on the old, and they're hesitating to go to the new. But what does it mean, new? It's not really new what we want to introduce you, because photovoltaic is not new, wind is not new, hydro is by far not new, Yeah, so we are more and more coming with the renewables also in the commodity. But we have challenges, and the challenges you see here on the screen, it's of course customer behavior. Yes, we cannot influence it, but yes, we see also customer behavior is changing very dramatically. We have this big data subject to discuss. Of course, I'm a technician, I can tell you, I'm very much appreciating to get data as much as I can. But data mining is very challenging. Distributed energy system, it's increasing the complexity. You can see it in the picture here. We have a lot of smaller and smaller revenue and energy generators, hopefully also revenue generators. And these are causing challenges also in stability, frequency and voltage stability challenges. We have shorter market time intervals, as you know, and capacity constraints. So we cannot very much influence as Siemens the customer behavior and the market intervals, but all the rest. And if I want to put buzzwords on, it means we are speaking about digitalization. You can see it all over the Siemens booth here. We are speaking about MindSphere, about the cloud and all the buzzwords. We are speaking about smart distribution. How can we distribute and control best? And of course, to create the best stability. We all hear this fear, especially from the more conservative guys. Blackout, if we are going for renewables, then we are facing the danger of blackout. No, it's not the fact. We have a lot of tools to ensure stability. And responsiveness, it's all about communication. So we have to ensure real-time communication and get very, very short signals back, responsive back from our energy generators. So looking into the future, so Bloomberg is saying, if you are looking for a long-term view, and long-term means 2040, it's really long for us. So imagine that. Nobody knows what is happening within the next 2-3 years, but here we are speaking about 2040. But what they are saying, and by good reason, is renewables will play the dominant role. And they are doing it already today, and that is the surprise. So what we see here in the invest, $12 trillion until that point for invest in all the energy generators. That's a big number, with 12 zeros, and you cannot imagine. Solar will be dominating, will be much more installed than wind. And that's not a surprise. We can see it also in short term. If you're looking to 2022, then you see also here in the figures, I don't want to go too much in detail, you see it here, it's self-explanatory, that solar is dominating. And the reason is, of course, the cost. It's not because people want to be very green and they love solar because it's so green and so nice. No, it's simply the cost. And that is the business driver and the driver for the installation. The PPAs since 2016, they go down dramatically. And you cannot generate energy cheaper than with, in utility scale, than with solar. And that's a fact. That's a simple fact. And I will explain you also later on why. Another good graph is on the left-hand side, where you see that the size of a single PV plant has been increasing year by year, dramatically fast. And that was, of course, driven by cost, dollars. That is the language we have to speak. And this is the only way for success, to keep the cost down and to be able to offer low PPAs. And just to give you an imagination about power plant utility scale, PV power plant utility scale. 100 megawatt means 240 soccer fields. And we are speaking today about gigawatt PV power plants. And you see the largest one in China had 3 gigawatt in 2018. So it's an incredible large PV power plant. And I can tell you, if you are flying over that with a helicopter, it takes a while. Yeah. And here you see again also that the records are depending on the countries. We had 35 in 2060, 35 US dollars or 3.5 US dollar cents per kilowatt hour in Mexico. In Chile 2.9, in UAE 2.8, and today we are below 2 US dollar cents per kilowatt hour or $20 per megawatt hour. And what is the reason for that? The modules, the PV panels, of course. The prices are dropping down dramatically, especially now after the announcement from the Chinese government saying we are now reducing our plannings for the utility scale installations in PV power plant. But what is happening now afterwards? They are reducing dramatically, more than 10 gigawatts less. What is the effect? The effect is the module suppliers, the PV panel suppliers, they cannot scale their manufacturing sites so easily like in many other industries. So they have an overcapacity and they have to sell it. They have to keep up and running the big machines. And that means they are going into other countries now offering that. And there is an overcapacity in the market, and that means the prices are dropping down dramatically for the PV panels, and I can tell you that was more than 25% since beginning of this year. And it was low already. But all the rest, if you are just highlighting this, so the PV panels, it's one part, but all the rest is financial engineering. And what we see is also a strong competition among the EPCs and the IPPs going for providing the lowest PPAs. And they are going in high risk now. Yeah, it means return of invest. They're expecting much less than before. Or the validity of their offer is going not only for 15 years, but for 25 years. So it's meaning they are going for a higher risk, and that means also due to the strong competition among the IPPs and two less projects available in the market, developed in the market for PV, the prices are dropping down. And here are the projects in the so-called solar belt. So you can download this map from Wikipedia. It's not a secret. It's simply the solar irradiation all over the world, and you have the most solar irradiation, of course, among the solar belt, so-called solar belt. And all these dots means here are the music players. It means the most projects you can find in these locations. Europe is coming back. France, Spain, Italy is coming back, Portugal, for example, and even in Germany they are discussing to go for larger utility scale PV power plants than it's limited today. Yeah. What is Siemens offering? It's electrical balance of plant. I just want to explain you what is the meaning of electrical balance of plant. Energy management is doing here the full job, meaning we are converting one form of energy to the other form of energy. We are taking the energy from the modules, the DC power, and converting it until it fits to the grid needs, even high voltage. And we have several elements here you can see. The key element is power electronic, that's the inverter. And we are calling that, and you see it here under number 2, the medium voltage inverter station. We are using a skid, an outdoor version, because it's simply the most cost efficient one. But that is the way we are approaching this. We will speak later on about string inverters as well, but I have only at all 20 minutes for that speech, so I have to speed up a little bit. Yeah, so sorry for that. Also for giving you the chance to ask questions. So this is what we are speaking about, and one part I want to highlight, besides the inverter, besides the power electronic, it's digitalization. And I love this chart. because the chart is giving you a little bit more than just levels. Yeah? It's giving you the insights, what do we want to achieve with this digitalization. So of course we have our different levels, and at the end the big data are arriving in the cloud, and we have to make the data mining, and we have to choose the right application. But what do we want to achieve? From my point of view, it has a lot to do with predictable analysis. It has a lot to do with weather forecast, for example, of course, renewables, PV, sunshine, so we should have a good forecast for that. We should forecast not only the harvest of energy, but also the dollars coming in. And if you are using storage, then of course we can make some good decisions, maybe automatically, with a good routine, saying, hey, we are making some peak shifting, demand shifting, to earning more revenue. So that would be interesting. Preventive maintenance would be very interesting in that field. Yeah, so all of that is addressed in our solution, and we have a specially designed power park controller, and we have a very good SCADA system, and we have some MindSphere cloud applications and all of that. What is interesting for me, if we are providing such a solution, let's say a 100 megawatt solution, then we have a revenue maybe about 10 million euros, roundabout, depending what is in. Then just 400,000 of that 10 million will be in digitalization. It's a small revenue, but it's very decisive for the IPPs or for the EPCs. So they are asking first, so what is your digitalization solution? What is your solution here with all the application? How can I control my power plant? Yeah? And then we can speak. Yeah? And that is more and more what we are seeing. And I can also tell you, looking to the inverter today is a computer. The half of the R&D staff is working on the software, the other half on the hardware. That's reality. And you see, I don't want to bore you with this slide. It's just a standard level. You have, of course, using a buzzword, the IoT, the Internet of Things. You have the sensoring, you are measuring data, you are monitoring, you are bringing that on the next level in automatic routines, controlling your grid, stabilize your grid. And of course, you want to have also the monitoring on people, so you are providing that over the cloud, over the MindSphere, in the right manner to the people, so they can control, they can have their reporting. All of that is standard today. The big differentiation is, of course, the how you are doing that, and how comfortable it is, and how secure it is. So looking to the scope again, the upper part is standard EPC. You see all these things about site preparation, security, fences, cameras, mounting structures. By the way, mounting structures are getting more and more interesting, because what I see in big power plants is almost everywhere tracking systems. So they are enabling the modules to follow the sun, and a one-dimensional, one-axis tracking system is in most, especially in the solar belt, in the most cases enough, and brings you two effects. One is you have a higher efficiency, so you are earning more energy, up to 20% more, which is really worth. And the other one is you are shaping the form, how you are achieving the energy, because of course in the morning, if you are having the right direction of the panels, you are achieving more in the morning and more in the evening, so the curve is going to be flatter. So we have, from Siemens side, we have the DC string combiner boxes. Sometimes there's monitoring in, so here we are collecting the DC power, then we are providing that to our key elements, the medium voltage inverter station. Then we have the medium voltage substation, as you might know, where all the rings are coming in from the RMUs, and then it's going to high voltage grid connection. Usually you have a 100 kV or 200 kV high voltage grid connection in large power plants, and of course digitalization by SciCam. That is maybe too technical. You see from the bottom side, you see the modules, and then it's going up in voltage, first in DC, then in medium voltage, 33 kilovolt in this example, and up to high voltage in this example, you see 115 kilovolt. That's a standard single line diagram, very simplified, and giving you, the technical people among you, an impression how we are thinking and designing. So now coming to a trend we see very often. It's a trend between central inverter and string inverter. Again, the inverter is the key element. It's round about 60% of the complete invest of an electrical balance of plant. So you should take care for the inverter. And the inverter is, of course, the element which is very sensitive. And you have to control all these nice things over the inverter, like Q at night, reactive power. All of those things you can control with the inverter. And what we see today is a trend to string inverters. String inverters means you are placing a lot small inverters, thousands of them in a PV power plant. This means higher capex cost, but it means also in the total cost of ownership that it might be profitable, because if you have a failure, only a small segment will fail. It's clear. If you are going to exchange, you don't have a big spare part management. You are just exchanging the complete inverter. You are not repairing anymore. And if you are going to install, you don't need big cranes and big machines. You can do it with 2 people. And that is of course, a calculation. You have to do it case by case. What we see today, there is a need to offer both string inverters and central inverters. Central inverters we will see for sure for the next 10 years. And there will be also more development to make it cheaper. The capex is a decisive point for central inverter. It's much lower than string inverter. But the OPEX and all the other parts, preventive maintenance and so, are lower in string inverter. So case by case, you have to calculate if this or that is more profitable. And a little bit more technique, if you allow me. 2 level, 3 level, we are speaking only about 1500 volts today in the PV area. I still see here and there, for example, in Taiwan, I got recently a request for a 1000 volt PV power plant. This is not what we see in general. In general, we see 1500 volts. If you're going to 1500 volts, then you have to go to a 3-level inverter. Please take care for this IGBT solution, otherwise you will fail. And I don't want to bore you with that, but with that one. This is my lovely baby. It's called SiC, and it's not SiC, it's meaning silicon carbide. And silicon carbide is the next generation of semiconductors. It's much quicker, much more efficient, and you can see that we have a lot of good arguments. All of the values are better than with standard silicium IGBTs. And this is now coming up. I had recently a meeting with Infineon, and we spoke about SiC. The point was so far, so silicon carbide is existing since many years, since 10 years and more. But the point was it was not stable. So we had always a problem in shifting the parameters over the time. But now finally they found a solution and the special coating for that, and it's now going into series, and it will change dramatically the electrical balance of plant world. It means also it will give an extra drive to the string inverters, because the string inverters will become smaller and cheaper. Just to give you this relation, as higher the efficiency is, as less dissipation power you have, loss. That means you don't have the demand for cooling so strong. You can become smaller with your inverter. If you are getting smaller, then you are getting cheaper. And that is the relation we have to regard. So silicon carbide will make the inverters more attractive, especially the string inverters. But there is also some shadow side, as usual. Where sunshine is, there's also shadow. And in this case, it's a demand. What do we see today we have a big increase and big demand in power electronics for PV power plants, called the inverter. We see it also in wind. They need inverter as well. All the wind generators, they need the inverters. They need power electronic. The electrical vehicles, they need power electronic inside. All the same IGBTs and the lithium carbide MOSFETs. Yeah? All the same power modules. I have 2 minutes left. I'm almost finished. And storage solution as well, and the charging station. So we have a shortage in the market. Sometimes we have more than a half-year delivery time for power modules. So that is another point I want to give you as an information to regard about delivery times also of the power electronic. So that's all from my side. If you have some questions, you have exactly 1 minute. So we have this microphone. If you don't have a question, then we can go to the next speaker.
I'm sure there are some questions from the audience on this.
It was obviously clear enough. Okay. So thank you very much.
Well, maybe just...
Is there one? No. Yeah.
Can you hear me?
Yeah, if you can, a little bit closer.
Okay. My question is, how would you value supporting devices for these utility scale PV plants? I'm talking about more granular forecasting and measurement of...
So that was...
Okay.
Can you repeat? You are talking about...
How would you value supporting infrastructure such as better forecasting and sensors of irradiance for these utility scale PV?
Of course, in the hardware, it's not very decisive. Of course not. Yeah? But what we see is in the performance, it's very decisive. Of course, I can react if I have the right weather forecast. I can react, for example, in combination with storage. But also, if I have a bunch of PV power plants or in combination with wind, I can outbalance. If I have a warning signal early enough, a good weather forecast, for example, then I have the possibility to react on this. Yeah? Therefore, I really appreciate now that we have so much developments in predictive analysis, algorithms which are getting more and more smart and accurate to give us out of the history data, but also out of the weather forecast data, very accurate forecast for our energy harvest.
Thank you.
Is there any other question from the audience? If not, I have one short question, which is you've mentioned digitalization and digital services of large-scale PV as one of, let's say, key topics for you, for Siemens to focus on. Could you maybe highlight which services in terms of services towards grid operation, support of grid stability are being used in large-scale PVs today?
Yeah, I mean, what is first very clear, if you are handling with reactive power for grid stability, then this is something you have to control within, you have to manage that within the inverter. All the inverters are also able to act as STATCOMs, as you might know. And therefore the need for extra invest for a STATCOM is maybe not necessary. You can freely, today with a PQ curve, maybe the technical people among you know what it is, you can freely define the PQ curve. That is again very much dependent on the income of the energy, so also the weather forecast, digitalization again, so we are speaking about that as well. Another part about grid stability is very clear storage. Storage is a solution. You have to calculate how much megawatt hours you need in a park, depending on the flexibility you need. And that is depending very much also on the region where you are installing the PV power plant. Is that answering your question? Okay.
Sure. Thanks.
So thank you very much. people.
Yeah, thank you very much as well, Mr. Ilyachevsky.
Yeah. Have a nice
And-
day. Bye.
So I'm happy to announce the next speaker, Mr. Gregor Taljan, who is asset manager and smart grids expert at, or coordinating smart grids project at Energienetze Steiermark, which is the largest distribution network operator in Styria, at the southwest of Vienna. He will give his insights on lessons learned from smart grids projects at Energienetze Steiermark. So, Mr. Taljan, the floor is yours.
All right. Thanks, Anthony, for the nice introduction. Good morning, everyone. So my job today is to give you a glimpse overview about all the projects that we went through in our company. Like Anthony said, we are the biggest DSO for the state of Styria, which is to the south of Austria. Just so that you know, we are operating roughly about 30,000 kilometers of low, medium, and high voltage grid up to 110 kV. And we are supplying roughly about 500,000 customers. Just so that you will have the perspective, or that you know from which perspective I will be presenting our smart grid projects today. Perhaps before I begin with the presentation and with the design requirements, for your information, we have right now about 15,000 PV installations connected to our grid. That number was about 30 in 2009. Now you see that this rapid expansion has taken place also in our grid, and this is one of the most important motivations why we tend to get from this big bad utility from the past to new very flexible and innovative utility of the future. Before I start presenting our projects, let me just shortly go through the design requirements, which are from our side, from our point of view, very important and sometimes also forgotten if we are talking about smart grids. I think that CapEx minimization, this is self-explaining. I don't have to go into this topic any further, but OpEx minimization is, from my point of view, one thing that is very often forgotten. We have seen that many solutions are very complex or depending also on the communication. And we see a lot of potential in this segment, also talking about how those solutions are designed. And our focus or our objective is really the simplicity by design. Because you have to know that up until now we have laid cables into the ground which are there for 50 years, are very low maintenance investments, and we wouldn't like to expand our team for the maintenance in the future when we build in new innovative technologies. For example, I've put here two simple cases. One is that you can operate, for instance, the regulated transformer in the transformer station with local measurements which don't need communication, and this is kind of a simple solution, but it's also not. It's also very resilient in terms of communication. But you can run and operate the same transformer which gathers the measurements from around the grid. This solution is, of course, depending on communication and transmission of the data, and it's less resilient, and it does for us as DSO not that attractive. Now, moving to the Smart Grids project, I will present, I think, 4 or 5 of them that we have done so far in our company. When I came to the company in 2010, we had already big difficulties with hydropower in the northern part of our grid, and we were looking for solutions which were cost-effective against classical grid expansion. And in the first project we did was that we actually developed a concept of online monitoring of a medium 30 kV voltage grid, and we actually implemented also remote set points of the power plants that we have in this grid, and we are with this concept we were able to gain additional capacity for roughly about 5 MV. I think that up until now 3 MV has been connected, which was not possible beforehand. The project is completed. We now see all the power plants and all the measuring points in the grid in our SCADA system, which was not the case before. And along with this, only with this implementation, we were really successful by gaining this additional capacity. Now, the next project that we entered was an EU project called Increase. There were several pilot projects, but our focus was mainly on phase balancing inverter development. Because what we have seen, this project started 2013, I think, and we up until this date we have had many problems with single-phase PV inverters. And this project was done to motivate firstly 3-phase inverters, and then to make those inverters even smarter by making them phase balancing. I hope you understand the concept. The inverter simply chooses the phase that is the lowest in voltage and tries to put the electricity into this phase, and this way balancing all 3 phases, which helps a lot in gaining additional capacity in the low voltage grid of DSO. Now this topic is perhaps not that relevant nowadays, because almost all of the PV inverters are 3-phase, at least in Austria. But there's another topic coming up, and this is the e-mobility. And in this spectrum, 3-phase systems are not standard. So why I'm presenting this slide is because I would like to stress the importance of 3-phase charging stations in home, at home with the customers in the future. The next project that we made was the virtual power plant for the DSO. The idea was to combine a market-oriented virtual power plant with DSO with some DSO aspects, so that the DSO would see what the market operator is doing. This is increasingly getting important because, like we heard before, the customers are changing their behavior, which means that they are also changing their load profiles in the end effect. And and what we are also observing is that many aggregators are switching our customers, which additionally means that our grid loading is not as constant and predictable as it was beforehand, but is changing rapidly. And these changes are very important for us in design of the grid and for the operation of the grid. And that's why this project was also important for us, because we wanted to see how we as the DSO can get the information from the aggregator into our SCADA system, and what we can do with this information. The last bullet is also, from my point, very important. One of the results of the project is also a market design concept, which focuses on the idea that we as DSO can operate or should operate the VPP infrastructure, but not the market-oriented part of it, just the infrastructure, and every supplier and aggregator should have the access on same terms to this infrastructure. The next project, this is our currently our parade project. I'm presenting almost weekly. It's throughout Austria, but also EU-wide. This is a project called LEAFS. It's a nationally sponsored project and is about how the flexibilities could help us DSOs in the future to better control and manage and plan our grids. It's a consortial project. We have a large consortium. We have 3 different pilot cases. Two pilot cases are about cloud storage, how you can connect many different household or home storage systems into cloud and centrally control those storage systems. And our pilot case is mainly about community storage, which means not storage on a household level with a customer, but larger utility scale, so to say, storage that is directly connected to the grid. What is the idea? We as DSO see the storage technology as an additional alternative to usual or classical grid expansion in the future. And we wanted to test this technology to see how it can put another advantage for us in the operation of the grid. What was also the idea of the project was the multi-use of this asset, of this storage asset, because we know that storage nowadays are pretty cost-intensive assets, and from our experience, we knew that we don't need this asset for 24/7, but only in some peak hours in the year. And we wanted to make this storage available for customers, for us, of course, and for the market in the winter, for instance, when we know that the customers are not producing the PV which they would like to be stored in this storage system, but storage can be thus placed to the market. Why central storage? We think that it's wiser to have one big storage in a community than 10 smaller ones. From the cost perspective, from the economy of scale, it's the communication and the maintenance is much easier. We can really use this storage also for our purposes, for the DSO purposes, and we can, or others can develop new business models. What is our speciality in this project? We didn't connect the storage centrally at the transformer station site, but at the end of the low voltage line. This is a very important thing because if you are doing or you are connecting the storage at the end of a line, then this storage can help you as DSO controlling the voltage on that line and increasing again the capacity for further PV installations. And we actually installed the storage on a line that was 100% taken by the PV installation. Oh, only 2 minutes left, so I have to go through quicker. And on this picture you can see also how this storage looks like. It's in the western part of Styria, and it's already been set up. We have rolled out smart meters so that we know at the storage location exactly when the customers are feeding in their electricity, and the same amount of this electricity is then stored into the storage. And when they are consuming their electricity back, then the same amount is injected into the grid again from the storage side. And of course, storage is always, the priority is always the grid control. Perhaps just short overview over the results. We have seen that the storage with real power we only use it for 10 hours a year. So it's a big asset once again, and we don't use it very often. But what's very, very important, and what I would like to stress, is that reactive power is of great use for us DSO. You can see that for 370 hours a year, the inverter is used, the storage inverter is used for grid control, but not with real power, but reactive power. So we don't need to put energy into the storage and take it out. For us, it's already a big advantage that we have inverter with this reactive power capacity. Grid expansion options, we did the calculation for that as well. Cabling would cost us in this concrete case roughly between 50 and 70,000 euro. We could install also a low voltage grid controller for 30,000 euro, and these costs are the limit of how much we as DSO are prepared to co-finance the storage system, and the rest should come from the consumers. And you can see also that all the consumers that are connected, we have 6 consumers with 10 PV installations. They store into the storage roughly about 10,500 kilowatt hours annually. Market design, this is also a very important slide. From our point of view, it's very important that we as DSO have in the future this option to invest into the storage solution. Of course, for us, this has to be more cost effective than the alternatives, but we need to have this option. And what's also very important is that we as DSO are not the only and sole users of the storage system. We think that storage makes sense only if it's used for multiple use cases simultaneously. For us, it's also important that we have the grid functions implemented in the storage control system, and that we as DSO can choose the location. This is very, very important, because it's not the same if you put storage in the transformer station, like I said before, or at the end of the low voltage line. Grid tariff is also very important for the future business case. We think that there should be a special tariff that if a customer stores in his community in the same low voltage grid into the storage and gets back the electricity from the storage, that he doesn't have to pay the full tariff, but reduced tariff, so that the whole system, the whole concept makes sense, like the whole household storage systems make sense right now. In short, the central storage should be considered on the same terms as domestic storage systems. And we also think that tax and renewable support exemptions should be put in place, like with smaller storage systems. Just shortly, because I think I've run out of time, about our next step is the LIFS 2.0 concept. In this case, we are going to use the blockchain technology, and the operation is going to change in the way that we are going to operate on the forecast for the next day. And based on this forecast, we will define the need for the storage capacity for each individual customer, and this capacity will be assigned to the customer, and this process is going to take place really dynamically for every day for the day ahead. And in the blockchain, the pricing, capacity allocation, completion of the contract, all these functions are going to take place decentrally in the blockchain system. We would simply like to see how the blockchain can be the alternative to classical IoT technologies. And just shortly about local energy communities, only one sentence, our position is that it does make sense to build parallel infrastructure for the local energy communities, but from our point of view, the better option is to use the existing grid, but perhaps to lower the tariffs if the electricity is produced and consumed in the same low voltage level, for instance. But still we are working on two different concepts. The concept with the private lines, with direct lines, in the Feldbad project, and we just submitted a proposal for a project which is focused on these reduced local energy community tariffs. Thank you very much. That would be all from my side.
Thank you, Grigor. So I propose we have time for one question, if there is some. Guess we have seen quite some examples on how DSOs are looking for solutions to support grid stability, at least on the distribution network.
Just one short question about the technique. At the first thing with the capacity of 5 MV, you found like it was not used. What was the total capacity of this grid or of the pod? So to get like how many percent of the was the 5 MV?
Okay. So this is concerning the first project that I've presented, this one. Like I said, we gained an additional capacity for about 5 MV of hydropower in this grid, and originally we had 10 MV, roughly about 9.6, I think, originally, and then another hydropower plants wanted to connect it to the grid. And that was for us the point when we said that we have to do something, because otherwise we would have to put cables into the ground and make large investments to accommodate new hydropower plants. So we gained roughly about 40 to 50% with these projects in this concrete grid. And the costs were about 150 to 200,000 euros, which is far less than the line expansion would cost us in this concrete case.
All right. I propose to shift any other questions to the panel discussion. Grigor will be here at the panel discussion afterwards. Thanks again, Grigor, for your presentation. Yeah. And now I would like to introduce the third speaker. So we had the distribution system operators insights, and now we are switching to the transmission system operator. So I would like to introduce Mr. Milan Vukosovic from Austrian Power Grid to give us his insights on how to ensure grid stability on a transmission network in case of high penetration of renewables. So the floor is yours.
Thank you, Mr. Chairman. Welcome, everybody. As already mentioned, trying to give you overview about the TSO activities, TSO Austrian Transmission System Operator, APG. And I think this is a very good follow-up related to the presentation that we have from the DSO side now. So I would like to tackle three main topics. I think the most important one is how to efficiently integrate renewable energy sources in the transmission network, how to coordinate remedial actions among TSOs in case the grid is not sufficient enough, let's say, to cope with the problems. And at the end, I will give you really a practical overview. What's the everyday business of TSOs, how we are solving the grid congestions, which are the problems we are coping with based on some real numbers, so that you have really a feeling direct from our main control room in the southern part of Vienna. So first of all, about challenges and related to the integration of renewables, you can see on the picture on the right side, we have a huge amount of renewables integrated already in the system, but they are integrated in a particular locations, especially in Germany. We have almost 100 gigawatts of solar and wind energy. In Austria and Switzerland, we have pump storage and hydro potentials, and in Italy, we have also solar and wind. So what we are having as a problem is expansion, as I said, of renewables. There is a priority in production, even it's not needed. The problem is how to cope with very fast ramps. We need a regulation reserve, so the keywords are ramps and volatility. And we also need coordinated remedial actions, also strategic reserves, in order to reserve conventional capacity to solve the congestions which we have in a real time or in planning phase. There are uncoordinated national incentives, which leads to the market distortion. We saw it already. There are feed-in tariffs, sometimes not even market-based. There is a price signal completely missing out of the market where to invest the new power plants and where to also, I think, strengthen the grid. We have difficulties because thermal units, conventional one, are out of the merit order of the market. They are being disconnected, decommissioned, and we have a problem really to have capacities to solve the overloads in the system, which we are going to see later on. As maybe you might think that the transmission network is going to lose on let's say, not be that important in the future. This, I think, picture shows you completely the opposite. You can see that in the last 9 years we had an increase of 40% of the energy transmitted over our high voltage system. So it means actually that with new renewables being connected at the network due to its volatility, we are going to have a need for a stronger transmission system being built and operated by the TSOs on a coordinated way in Europe. You can also see some plans. What's planned? This is 10 years a network development plan of the NSOE for the time plan 2025-2030. And for particular for Austria, you can see a new projects which are planned. Especially the most important project is the Salzburg Leitung, so the connection towards Germany, which is going even more to increase the capacities towards Germany and improve, let's say, already very strong connection with this country. Nonetheless, as the network investments has been currently delayed, you can see what does it mean from the perspective of the total costs. Those are the total physical firmness cost. It means costs of redispatch and counter trading paid yearly by the transmission system operators in Europe. And as you can see, German and Austrian bidding zone, which was split from the 1st of October, has the largest costs because Germany alone pays more than 1 billion of euros per year for redispatch, and Austria is paying around 100 million of euros per year for the redispatch activities. And at the end, all those costs are paid by the end consumers. So it means if we would have a really strong network already in place, those costs would practically diminish. Yeah? And this is our aim, to have the projects which we agreed on beforehand put in place as soon as possible. Why we have such a cost is, you can see here what is going on in Germany. You have a market schedule, but due to the weak internal network in Germany, the energy cannot be transmitted, and you need to reschedule the generation park. You need to reduce wind generation in the north to increase the thermal units in the middle, for example, of Germany. And that, as I said, amounted to costs of 1.4 billion euros in 2017, and there is a curtailment of renewables in the amount of 5.5 terawatt hours per year. So this is a large amount, and as you can see, comparing to the wind energy generation in Austria, it's more or less the similar, I would say, 1 terawatt hour additional on top of that, but it's really a huge amount what we are talking on here. Costs of Austria are also increasing with the time. You can see the actual status. Part of our costs, which we are paying within Austria and consumers, is around 100 million of euros. As I said, was the last year. But the larger part of redispatch activated in our control area is mainly for the external, let's say, needs, mainly for the German needs. And as you can see here, last year it was more than 300 million of euros that was paid to the power producers in Austria to redispatch the power plant. And this trend is not even linear, it's more or less exponential in the last years, and you can see that the network plays really an important role to integrate renewable energy sources. What I would like also to discuss and let's say mention a little bit here are our obligations towards the fourth energy package. We are currently on a TSO side implementing third energy package, network codes legislation, and we have some, let's say, requirements out of it. We need to, on a coordinated way, together with our companies, which are the regional security coordination centers. We have in continental Europe 2 of them, Coreso and TSC-Net, which are taking care that all the services which needs to be done in a coordinated way by TSOs are centralized and performed, let's say, from the central place with the IT tools developed together with the TSOs. We are developing different methods, putting them in place and fulfilling European legislation when it comes to the energy market integration. I just mentioned here some of the articles. I think it's more just for your information. What we are currently working on is to develop the central co-optimization function to more efficiently implement non-costly remedial actions together with the costly remedial actions, which means phase shifting transformers, change of a network topology, integrate bits from the redispatch energy market, from the counter trading, to put this all together, try to solve this complex optimization problem for 24 hours, yeah, with the intertemporal constraint in order to decrease costs on a general level in Europe if let's say the activation of a congestion management measure is needed. So you can see this complex optimizer. It's going to solve all the violations which are, let's say, identified by the TSOs in the different steps, and the outcomes are, let's say, the new load flows, costs, and volumes in redispatch, which needs to be, let's say, activated. This is just a small example that you know how it works. Below you can see 110 kV lines, 2 of them in parallel, which are overloaded in a contingency case, so the grid is not n-1 secure. And first of all, if you want to activate, let's say, the change high voltage DC settings, you end up with one relief. First of all, the lines are relieved. You go further on with the changing of PST taps. The lines are even more relieved, and at the end, due to the activation of redispatch, you go below, let's say in this case, you go to 106% of line loading in n-1 case, and you can really see that due to the coordinated activation, you try to minimize cost and put, let's say, everything in place on the most economically efficient way. So this is what we are doing currently. We are implementing this project. It's foreseen to be implemented next year and operated by TSC-Net and Coreso, our companies which are having the seat in Munich in Germany and in Brussels. And when it comes to the current practical experience related to the planning execution of the remedial actions, I would like to show you everyday process that we are doing in our companies. We are trying to create models to forecast the situation for tomorrow. What we need for that is we need a forecast on load, which is being made by the DSOs, TSOs. We gather this data, put this in the model. The next in the model is, so it's load and generation. It's put in the model. This is a forecast data. And we also need a forecast, so on the network topology, we need to disconnect some line which are in let's say, in the maintenance periods and so on. So we merge all those data together, and we prepare so-called individual grid models. So every single TSO completely independently from the other one. We send this to the central places, and this is Coreso and TSC-Net, as you can see here. Different transmission system operators are sending this, and those models are then merged. We have a common grid model for Europe on a day-ahead level, and out of this model we are performing load flow calculations and contingency analysis. We are identifying the hotspot in the network every single day for every single hour, and we are agreeing on the remedial actions which we need to apply to change the schedule of a power plants to solve those problems. If the problems are not solved, you know what will happen. We are going to have a cascade and in the worst case a blackout in Europe. So this is really an everyday business, and you see it, you already saw it in the prior slides. We are talking here about costs in Europe of more than 1 billion of euros per year, which has been paid to the end consumers to solve those problems. This is a practical example. 24th of August, we have a pretty sunny day in Germany, and also windy one, I would say. This is an average on wind and solar being produced, so energy being produced in Germany. On a Danube river in Austria, we have around 900 megawatts. And there was a low wind generation in Austria, yeah? As you can see here. But the thing is that due to the market needs, cheap electricity from Germany has been imported towards Austria, and you can see the 3 hotspots here shown and identified where we have violations of almost 140% and -1 violations. So we need to solve this. We need to order redispatch in Austria to increase generation, go upward, yeah, and at the same time decrease the generation in Germany to cope with those very critical situations. So what have been done is, you can see the schedule from Germany, which was 7.6 gigawatts in one particular hour, going over the border. And we activated redispatch in Austria, mainly thermal power units, and we regulated back. So at the total, there was a 4.1 gigawatt of redispatch being activated. You can see below on the diagram, thermal and hydro units been activated. The energy production in Germany has been decreased in cooperation with our German colleagues, and we solved those critical loadings of a network for this particular hour. This is everyday business. This happens more or less every day, and I will underline it one more time. Maybe I'm getting a little bit lost on this point, but I would like to underline one more time: the transmission network reinforcement is the most important measure to solve such a critical situations in the future. At the end, what we have in front of us, and I would like to sum up, let's say, key points and key messages out of the presentation. What we can expect in the future when it comes to the renewable energy integration into the transmission system and integration into internal electricity market in Europe. What we see now is in 2017, we have installed capacity of 5 gigawatts, around 5 gigawatts in Austria of wind and solar. This is mainly wind, as you can see, and the trend is increasing starting from 2011. It's almost 4-time increase. But what we have is a very, I would say, challenging plan in the future, year 2030, where we would need to have a coefficient multiplied with 6. It means 12 gigawatts of photovoltaic and 9 gigawatts of wind. And you can see that already now we are having problems with the renewables integration in Europe, and particularly in this case in Austria, when we are talking about such kind of numbers, you can really think what does it mean for the end consumers from the new network investments and so on. So to summarize, let's say the main messages one more time, what we need in order to integrate successfully renewables into the transmission system and to ensure successful transformation of energy system is, of course, first of all, I mentioned this, is transmission system reinforcement. This is a must. It means that the projects which are already been, let's say, agreed on, planned, and approved by the national authorities needs to be put in place as soon as possible in order to have really costs for the end consumers decreased on a proper way. What we need is also a flexible load. We already heard it a few times today. We need the demand-side management measures, so really flexible units aggregated over the pools and aggregators, which are able to react on the price signals the signals, for example, for emergency cases, also from TSOs, to regulate up and down and to balance the system if it's needed. And what we already have are, let's say, mid to long-term storage systems like a pump storage power plants in Europe. We need more short-term storage facilities like batteries or electrical cars and so on. And we need also new technologies. I put here just power to X. You can think about it, what does could mean. Anyhow, in order to satisfy very volatile renewable infeed, we need the measures to cope with this and storage facilities. And at the end, if the transmission system reinforcement is not being done on a proper way and not in a timely manner, the TSOs need still possibility to get into contract over the thermal units, mainly to get the conventional power plants to cope with those overloadings in the system, like we are doing nowadays. And of course, we need to have a redispatch and counter-trading mechanism. We are currently working on it. I show you the project with the central co-optimization in Europe. We are going to have this in place to further decrease costs of redispatch and counter-trading activation in the future. And what we have already in place in Austria and all other European countries is a pretty mature and developed balancing market where we are having tenders for primary, secondary, tertiary reserve, now called frequency containment reserve, frequency restoration reserve, and replacement reserve. We are integrating those services over the markets, connecting the different countries, and ensuring that due to this, we are trying to further ensure more liquidity and reduce the total cost of the system. So I think the message is at the end pretty clear. In order to integrate renewables, you need a strong transmission network. You need a pretty good coordination and efficient coordination among European TSOs. We are already ensuring this and putting it even on a more higher level, I would say. Will be done with the fourth energy package anyhow, which is currently in preparation and negotiation among member states. And we also need the balancing services to cope with sudden, let's say, increase and decrease of a load or generation rarely, let's say, in the system. So I would like to thank you for your attention, and in case I think there are some questions, I don't know if there is the time to take them now. Yeah, thank you.
Indeed, thank you very much. I guess there are some questions. We can for sure handle one, and there is room for during the panel discussion as well. Is there any questions from the audience? Maybe I would like to come back to one question since it's has been in the news lately, and there has been this recent decision about splitting the German-Austrian market. From your point of view, to what extent does this relate to the integration of renewables? Or to what extent was this, let's say, due to the congestion and driven by political decision makers? Maybe your view on this.
Yeah. Thanks. I think this is a very hot topic, especially in Austria lately. We implemented congestion management measures on the border between Germany and Austria from the 1st of October. That was a decision from the European regulators, from ACER. We need to follow this. From my point of view, it's pretty related to the renewables integration, as well as very weak networks, mainly within Germany. Germany is one bidding zone still, but you saw it in the last years. The problems that we had and the increase in the costs can only be, let's say, correlated with a dramatic increase in renewable energy power being, let's say, installed in Germany. And of course, there are different measures how to cope with this. Either you build your network properly, you put your new transmission lines, and then you don't have a problem. But this process is taking quite some time. In order to get all the approvals, I know that our German colleagues are having also problems with this. Similar is in Austria, by the way. The second possibility is to split and change market design, so split zones and change bidding zone structure. This is what has been done currently. on this case. And the third one is to go on, like I show in the slide, and spend €1 billion every year for redispatch and do nothing. And this is, I think, no-go. So there are different measures how to cope with this, but I would say that one of the main reasons, if not the main reason, is renewable energy integration followed by the unsatisfied level of transmission network reinforcement. Yeah. Thanks.
Okay, thanks a lot again. Yeah, a round of applause. All right. Then I would like to introduce the next speaker, Ms. Natalia Romero from TU Delft. So, who is, well, actually connected to the last presentation on the use of flexibility, redispatch, but maybe on somewhat different level. Some insights on a toolbox for the optimal use of flexible loads. So, Ms. Romero, the floor is yours.
Good morning. Thank you for being here. Andrew, thank you for that introduction. And actually, also, I think that your presentation was a good introduction for this presentation too. So I come from the Delft University of Technology, and is from the Department of Computer Science and Algorithms. So we're developing and integrating different algorithms that are already there on a toolbox that will help us to use a lot more of that flexibility on those loads. This doesn't just follow price markets or day-ahead markets, but the idea is that we also want to optimize that offering the reserves. So for regulation down or up, to make sure we keep the balance between the supply and demand. So we think that this toolbox is a great tool for businesses that can offer that flexibility, for investors in those businesses, for transmission system operators, for distribution system operators, also for regulation analysts that are trying to inform those new regulation decisions. And here start. So the objective of these planning algorithms, the idea is that we have this flexibility that needs to be a schedule. There's electric vehicles, there are greenhouses, the traders themselves create flexibility and liquidity in the markets. And then all these parties have an economic incentive, right? It's either reduce costs or make more profit. And these economic incentives are there also to help balance the grid at the end. And this is how is the contribution for grid stability as well. So just look at like all the different markets where flexibility is valorized. So there is mainly day ahead, the intraday market. There are the balancing markets where you can procure reserves for balancing the grid. And there's also, of course, the balancing markets where the imbalances are settled. And in all these places, there is a different way of like how you would pay for that flexibility. But then there's a lot of uncertainty. So this figure is from the Dutch market. Is the imbalance price, so it's the real-time prices. These are 3 days, the same month, the same year, the same day of the week, but different weeks. And you can see that the prices vary a lot. So when these algorithms think about like the mean of all those prices, you'll see that it will be very easy to be off, and it will not be that profitable for a business that is trying to offer flexibility. And in the group, we focus a lot on like how do we capture that uncertainty for those planning algorithms. In addition to that difficulty, it turns out that markets are designed differently all across just Europe. So this is a figure from ENSO that shows, for example, for the research markets, there is a requirement, a minimum bid. Well, in all the different, give you an idea of how different it is in the different countries. There is also a difference in the time length that you commit those reserves. It's also varies across all of Europe. So then the idea with this toolbox is that, well, we want to explode that flexibility, but there are a lot of challenges for that. So what is already there? I mean, there's a lot of EV and flexible load scheduling based on expected prices. But that usually is not the best because I show you how much uncertain those prices can be. There are also good models that capture that uncertainty. I would say not for all type of markets. And then there's also models that do the aggregation, right? So like not just one load, but many loads, because an EV, for example, like the charging speeds are within like what, 7 kilowatts, 22 kilowatts now, the fast charging. And then we're talking about like, I think the numbers were 4,100 megawatts. So we definitely need to have models that are aggregated and of course that can deal with that in a good time. So our toolbox, what is the additional thing that we're working on? So one is that to provide regulation down, to provide reserves, you need to capture a lot more than uncertainty. And we've been working on making sure that it is competitive to make reserve bids. So those sources of flexibility can really help balance the grid in that way. Then the models also, we are working on like designing all the different features that the markets can have. And also in a platform that is compatible for different models, is compatible for different markets, and it has a benchmarking tool. So like if somebody that wants to get into the business for a DSO, transmission system operator that wants to use these models, they have a way of thinking, is this the best way to do this or not? So it's a way of measuring what is the best method to use. So like I said, so the toolbox is, the idea is that it's very modular, that we want to compare different solution methods for the problem. We can change the market configuration. So how the bids settle, how you pay per capacity or you pay per energy. What is the timeline of your bids, for example? And also we want to make sure that it's easy, extendable, and customizable. So because of the modularity, then if you want to adapt it to your specific needs, you can also do that. So this is an idea of like kind of the input that you can have. So I mean, input and output is mainly like the files that you need. The output will be like what do you want to see from these results. And then as you see, I mean, there are different features, like for example, like your risk adverseness of like how much you're willing to not fulfill the demands. For example, if you are an aggregator of electric vehicles, if you want to aggregate those loads in a certain way, if you have a specific kind of algorithm for that, you can also include that. I now want to go into like some of the kind of an example of what are these smart algorithms doing for somebody, for example, an electric vehicle aggregator. So let's say that we have an EV aggregator. We actually work on this with an EV aggregator. So that's why a lot of our examples right now are for that, but we're definitely extending it for a different type of flexibility. So we have, for example, that they're trading right now in the Dutch market on a day ahead, but they want to also see the opportunity of offering reserves and if that's more profitable or not. So, and this is now the technical term for that, automatic frequency restoration reserves. And so this is the day ahead. Below is the price. And so you might not see the difference, but basically the lowest price happens from 1 in the morning to 5 in the morning. And that's when the EV is an EV of 7 kilowatt maximum charging speed. So that's when you would be paid to charge because you're going to get the lowest price. And then because you want to fulfill all the load, then you have to use the second lowest price that you have in the day. Now, if we want to move to offering reserves, it's a little more complicated because then you have to make a bid on the price that you're willing to offer that reserves. And then, of course, in each time, if it's a regulation down or if it's a regulation up. So let's see a little bit of like what I mean with that. So again, we have here the model of the day ahead price. And in the bottom figure, I'm showing you like the price bids that the aggregator would do for that EV. In the figure up, it's a charging kind of plan. So the blue dots were like I was planning to charge based on my buying the energy from the load. But when I have, for example, a cross red, that means that I'm going to offer reserves up. So that means that if I'm charging, I'm willing to not charge at that time if I'm going to get a better payment. And then on the orange one is that I was not going to charge, but if you're going to pay me enough, I'll be willing to charge, basically. And then that's just how we can monetize that flexibility that a storage unit can have. And the most important thing is that, so the red line at the bottom figure will be the actual real-time price, so the imbalance price, which will determine how well you're going to get paid. And then the black line in the top figure is actually how the EV will be charged based on whether those resource bids were accepted or not. So I make a bid, I offer that I'm going to help to balance the grid, but then it's up to the transmission system operator to decide if they really need to use that reserve. And this accounts for that uncertainty too. Now the second case is something I think it comes along with the discussion between the coordination between the TSOs and the DSOs. In this case, I'm thinking of like 10 EVs. They're all in the same neighborhood. In the Netherlands, I think DSOs think about like 1.5 kilowatts per household of capacity for planning the grid. So if we're thinking of a 40 household feeder, then we're thinking about 60 kilowatt maximum capacity for those, if those 10 EVs are located in that. Now, this is a 20% EV penetration, so that's big for a standard right now. But I mean, like, this can happen in the future, right? So if these EVs are charging at the best price they can find, then you can see that they will likely going to go above that maximum capacity for that feeder on just one night charge. If they're all following that best price, right? So we are incorporating the algorithm, also the capacity of enforcing that grid capacity. In this case, it's a flat saying that the EVs cannot charge more than 60 kilowatt, but you can do this dynamically. And then it still optimizes the benefit for the aggregator and for the user, but guaranteeing that the grid can stay stable within like that limit. So like in some way helping to manage the congestion that can happen at the local level. So, and with this case, I'm just opening up some discussion too about congestion management. So there is the tendency to think about what we have been doing in the past, which is reinforcing the power grid whenever we start having congestion. But then the question is, like, could we use solar methods? And some of the things that we are looking at is, for example, well, what are the technology, information, or control solutions that we can do? Can we establish some like autonomous control to make sure that this doesn't happen? If we can do it with algorithms, we should be able to do it also with technology. There is also the options of pricing that network capacity, pricing the contribution to congestion, pricing flexibility, which is something that is being extensively discussed in the Netherlands. And then also redesigning or creating new markets for that flexibility to manage congestion, of course. So closing this presentation, I mean, I presented here some of the toolbox that we're working on, that we're developing. This is an open source code. It will be an open source code. The idea is that it can be used by business with flexible loads and their investors, aggregators of flexible loads, also analysts for policymaker development, transmission and distribution system operators. And future plans is that we'll be conducting a workshop, and we'll have the launch of the first version. Right now we're estimating it's going to be January or February. We want to have participation from all these different potential users, because that will help us to have an even better version too. And we're definitely going to use it to keep extending to different market models. We already cover a lot of them, but we can still add some, and algorithms. And of course, we want to use it to analyze, compare, give ideas about what is the best market design to exploit that flexibility. So the idea, we've seen that, at least in the scientific literature, there is a lot of algorithms, but they solve one single problem. The idea is that this is modular, and like you can use it for different purposes, to ask different questions. You don't have to be an expert in planning to be able to start asking these questions. So if you go to this URL, you will give us your contact information so we can let you know if you want to know about the workshop, if you want to know about the toolbox, or any of our different publications in this topic. So this research is financed by the Netherlands Organization for Scientific Research. And well, thank you.
Yes, indeed. Yeah, thank you very much. Is there any questions from the audience on this topic? Yeah.
Hello, I have a question. Have you seen or do you foresee market speculations? So they buy energy, and then when congestion is ahead, then you don't have the capacity available.
So we in the Netherlands there is a discussion about flexibility markets, and particularly we're looking at algorithms to show that that's a problem. That could be a problem. When you think about a market and you have, for example, an aggregator that has enough market share that they can cause that congestion, that can cause problems too. So part of our work when we're looking at like capacity costing the capacity network and tariffs is because we're thinking about alternative solutions to that. Because we're concerned about like if you don't have those local markets well designed, I mean there's already speculation in the market, so you need that. But if you have a party that has that market share that can cause that congestion, it can cause increase in that price, that can become a bigger problem and bigger cost. So yes, we see that that could happen, and that we're working on like trying to expand that debate so that doesn't happen for regulatory purposes. Thank you.
Thank you.
Any other question? If not, there will be the opportunity during the panel discussion because Ms. Romero will also join the panel discussion afterwards. So thanks again. So then we are on a half an hour break, or let's say 26 minutes break, and we will start again at 11:30 on this. So.